Hey everyone, welcome back to another session in AP Calculus ABBC course. And in this session, we are going to cover few topics in the Unit 5, which is Analytical Applications of Differentiation. This topic is very important and it weighs around 8 to 11% of the BC student exam and 15 to 18% of the AB students. Okay. So, in order to connect with us, you can contact us on this number. If you want me to have a one-on-one tutoring session or group sessions with you, feel free to connect with us. Okay. So let's start with Unit 5. We have the following subtopics in the Unit 5: analytical applications of differentiation, like mean value theorem, extreme value theorems, finding the optimal solution, maximum or minimum value, sketching the graph with the derivative. If the derivative is given, how to find the original function, right? We have so many things to cover in this unit 5. Okay, so let me give you some basic details of the derivatives and how we can use that on the graph paper, and later we will see its application as well. So consider on our Cartesian system, we have this is our x-axis and y-axis, and the point of intersection is obviously origin. Now, we have a function y is equals to f of x given by this. Okay, so the equation of this function is y equals to f of x. Y is a function of x. So, what do you mean by zeros, critical numbers, increasing, decreasing nature, where the function is increasing or decreasing? How can we find that using graph? And also I will do it with the mathematical expressions. Okay. So, because we are going to use the analytical applications. Okay. So, here, what do you mean by zeros? Zeros are those values of x where the f becomes equals to 0, right? So, x values for which f of x becomes equals to 0, then whatever be the x you get as the answer, or simply your x-intercepts, right? Or you can say x-intercepts are the answer. If the graph is given, you can simply find the x-intercept. So let's call these as A point, B point, C, this is D, E, and F. Okay, these 6 points, right? Whatever be the x value at these are your zeros. Okay, so in order to find that, either you can use your GDC for giving you the values, or you can draw the graph and find the x-intercepts. Next one is critical number. For finding the critical number, first you need to find the derivative. So find the f dash x and put it equals to 0. The values of x you got from here. Okay, those x values for which the f prime x equals to 0 gives you the critical number. F prime x equals to 0, or we also call it somewhere it is not defined. Okay, f prime x is not defined. At those points also we get the critical numbers. So in this case, let's say, what are the points by the way? Here, because f prime x equals to 0 means you can draw a tangent line parallel to x-axis at those points. So this is one of those points. Okay, so let's call it G point. Like this, we have other points as well where the derivative is 0. So G, let's call it H, I. There is one more point, by the way, where the function at this point. Let's call this I, because at this point, actually, the derivative is not defined, because the tangent line will be perpendicular to x-axis. I will discuss that also, how to find these. So I, J, K, L, this is M, N, and O. Not O, O we already taken. So let's call P. O is origin. So at these points, right, from these points, we are getting the critical numbers. The x values at these points are your critical numbers. So G, H, I, J, K, L, M, N, and P. M, N, P. These are the x values at these points are the critical numbers. Let's call it x equals to xi. Okay. Now, in order to find these values using the graph, what you can do? you can find the points where the tangent line is parallel to x-axis, or you can solve for f prime x equals to 0 if the equation is not, if the graph is not given or GDC is not allowed. Next, increasing or decreasing nature. As you can see, function is increasing sometimes and decreasing, like right here is you can see. So how to find those? From the graph it is very obvious, right? If you look at the graph only, it is very easy for us to find the points where the function is increasing in nature. As you can see here, for this region it is increasing, right, from for the values less than g. Similarly, for this h2, for this h2, j, again function is increasing. Similarly, for k2l it is increasing in nature. So graphical method is very easy. Okay. Similarly, for the values more than p, the function is increasing in nature. Okay. So here, how to check whether function is increasing or decreasing in nature? Graph, simple. It's very easy to find it from the graph. Just look at the graph. Answer. But if the GDC is not allowed, then what we can do? So here you have to find those values of x for which the f prime x is positive. If f prime is positive, function is increasing in nature. And if f prime x is negative, then function is decreasing in nature. Okay. So if you try to calculate the derivative, right, put it equals to 0 and find the using the graphical graph, okay, you can find the values where the function is increasing or decreasing, right? Okay. So for example, I'll show you here. You can simply draw a number line, mark those points. What are the points? G, H, I, J, K, L, M, N, and P. Okay. So your entire real number is divided into these many parts. Now what you can do is you can find the sign of f prime that we already covered in the last session. You can watch that session. Okay. So take any value less than g. Okay. X value of g. I'm talking about the x values, by the way. Okay. So you will find that the value comes out with a positive sign. So you can check for each of these. So here I will get positive, and from G to H, as you can see, function is decreasing. Automatically it will come with negative. Okay. Similarly, you can check for the others. So I to positive, positive to positive. See, positive to positive again. Then you will find it negative for this one, positive for this, K to L, L to M, L to M. It was positive, and M to N, sorry, L to M it is negative, M to N it is positive, so function is increasing in that region, and for N to P it is decreasing, negative, and after P it is positive. Okay, so in this way you can find the increasing or decreasing nature if graph is not allowed, finding the derivative. Okay, derivative positive, function is increasing in nature. Derivative negative, function is decreasing in nature. Now next thing is local maxima and local minima. The word local means in the neighborhood only. Okay, not everywhere, in the neighborhood only. So for the local maxima and local minima, you have to find those points where the, see, critical numbers, take those critical numbers, and you can check if the graph is allowed. Then it becomes very easy for us. What can you say about G? Obviously G is a point of local maxima. And let's take H. What is H? H is point of local minima. Similarly, J, L, N, right, these are points of local maxima. K, M, and P are points of local minima. So in this way you can find the local maxima or minima from the graph. But if you have to do it analytically, right, if the graphical methods are not allowed, so for that we have various methods, like we have first derivative test. and we have second derivative test for that I will discuss in the same session. Okay. So after that, next point is absolute maxima or absolute minima. Yes, absolute is only one, which value is the maximum of all the values on the entire graph that you have to find. Or absolute minima is the minimum value of the function for the entire graph. No matter whether you have a derivative equal to zero at those points or not, it doesn't matter. So from the graph, as you can see, of all the values, the graph is going up highest up to this point only. So here you are getting the absolute maxima. And as you can see from the graph only at k, right? The y value is as minimum as possible. So the k is also the absolute minima. It is one of the local maxima, but it is absolute, sorry, it is one of the local minima, but it is absolute minima also. P is only local minima. It is not absolute, right? So that's how we can find whether it is absolute or not. Local means in the neighborhood only, but absolute for the entire graph. Okay. Concavity. Next part is concavity. How to check the concavity? It's simple. From the graph, if the graph is, see, looks like this, and if you draw a tangent line to it, any point. So as you can see, the graph is above the tangent line. So we call it concavity up. But if you have graph of something and if you draw a tangent line at any point, the graph is below that tangent line, we call it concavity down. Okay. And analytically, if the double derivative, okay, that depends on the double derivative. If the double derivative comes out as positive, then the concavity is up. And if the double derivative comes out as negative, then the concavity is downward. Okay. You can choose any point. Okay. Let's talk about on this graph B to I. B to I. What is that? Concavity is downward. Okay, concavity is downward. So for I to J, what is that? Concavity is upward, right? Down and up. For I to J, concavity is upward. So at I point, function is not changing its nature from increasing to any other thing. It is increasing and again increasing, but it is changing its concavity at I point down to up. So these type of points are called points of inflection. Points of inflection. Okay. That's why this I is not coming in either local maxima or local minima, because this is a point of inflection. It is neither local maxima nor local minima. It is a point where concavity is changing, but nature is same, increasing to increasing. As you can see on the graph as well here, positive to positive, increasing to increasing. So these points are called points of inflection, where nature remains same but concavity changes at those. Okay. Now let's move to the next part. Application based problem. So I'll discuss the solution to this problem using the graphical approach as well as first derivative test as well as the second derivative test in detail. Okay. So it says find the height of the cylindrical can having the minimum amount of aluminium used to manufacture it, and the capacity is already given as 100 cubic inch. Okay. So what we have to find here, the volume is already given. If you see 100 cubic inch is the given volume. So volume is constant for that. Now this is find the height of that cylindrical can having the minimum amount of aluminium used, means the surface area is minimum. By looking at this, you can see we have to minimize the surface area. So always you have to find the function which is to be optimized, or either it is to be maximum or minimum. Okay, so this is function which is to be minimized in this case, right? So always find that function, convert it in terms of one variable. Okay, so if we have a cylinder, let's consider this cylinder having the base radius as r and the height as h. So we all know what's the formula for the surface area. Yes, it is 2 pi rh plus 2 pi r squared. It is in terms of both h and r here. Initially we have h and r here, but in order to convert it in terms of one variable, we need one given information, right? Because we cannot differentiate it at this point. First we need to convert it either in terms of h or in terms of r. For that I will use the volume formula. Volume is given as already 100, right? This is volume. Volume formula is nothing but pi r squared h, which is 100. So using this, first I will calculate the value of either h or r in terms of others. So from here, can I say, using this, can I say that my h is equals to 100 over pi r squared. Now substitute, plug in this h value back to this expression. So here, in place of this h, I will write 100 over pi r squared and simplify it. So what I will get, in place of h, put 100 by pi r square. R cancelled, pi cancelled, simplified, right? So we get something like this. Now our area in the simplified form is 200 over r plus 2 pi r square. This is the function only in terms of r. Now I can differentiate it with respect to r to get the critical numbers. You remember, we have already seen, first we need those critical numbers because our local maxima or local minima values lies at those critical numbers. Okay, so put this, find the derivative first. So using the power rule, I can rewrite this 200 over r, this 200 over r can be written as 200 r raised to the negative 1 plus 2 pi r squared. That is my area formula. Now if I differentiate it, means dA over dr. That gives me what? 200 as it is. For the r raised to negative 1, the derivative is negative 1 times r raised to the negative 2 plus 4 pi r. Okay, so simply use this in that expression. Here gives me this. So now let's write the a prime value over here. Okay, so that gives me what? A prime is equal to negative 200 over r squared plus 4 pi r. Okay, now in order to find the critical numbers, put this value equals to 0. This time put this value equals to 0 and solve for r. Either you can use your GDC, because this time it's a cubic equation, so it's good idea to use the GDC and solve for the value of r using either numerical solver, okay, or graphical method. For graph, you can find the x-intercept to get that, or numerical solver directly gives you the value. Okay, but generally you will get an easy expression, okay, quadratic or linear expression, if calculator is not allowed for that particular question in your exam. So here I got R as 2.5153 something using the GTC. Okay. Now that is R value, means there is a possibility of getting a minima or local minima or local maxima at this point. Okay. So for that you can, what you can do is simply use the graph, but like this, for the sign of A prime. Mark this point 2.515, right? And check for any value of r lying between these numbers. So take 1. Okay. In this expression, if I put r is equals to 1, what is the value? Check it. Whether it is coming out as positive or negative, that you have to check. So when I put r is equal to 1 over here, I'm getting negative 200 plus 4 pi. Obviously negative, right? So negative over here, and a value more than 2.5. Take 5. Okay, take 5. So when you use that, so you will get negative 200 over 25, negative 200 over 25 plus 20 pi. This value comes out with a positive sign, obviously. Okay, So positive. So what is that? That's your first derivative test. See, function was decreasing first, then started to increase. And there is this point, 2.515. Can you see this? Function was decreasing first, then starts to increase. That clearly shows this point is a point of local minima, right? It is going from negative to positive. That shows local minima. In other case, for example, if you have a positive to negative change, then that point is local maxima. By the way, not in this case, but that is the method. Using the first derivative test, that's how we calculate the local maxima or local minima from this sine graph. Okay, so it was decreasing first, then starts to increase after 2.515. So this point is point of local minima. Hence, we got the radius at which the surface area can be minimum. Okay, now what they are asking for? They said find the height corresponding to that radius where the surface area is minimum. So we proved surface area is minimum when radius is 2.515. Now plug in that radius value back to our height expression over here and get the value of height. H is equals to 100 over that pi times radius squared. So that gives me around 5.031 inches. So that is the height at which the surface area is minimum, volume is 100 for that cylindrical can. That's your first derivative test. I hope you got this. Finding derivative, put it equal to 0, check the sign of A prime, negative to positive or positive to negative to check the local maxima, minima thing. Okay. Second method. Second method is graphical approach. So graphical approach, you can simply draw the graph in your GDC and you can sketch it. Sketch the graph. You know, there is a function already in your GDC where you can sketch the graph and you can find the minima point. When you do it, you will get your answer. So in your, you can move that point, go to menu, then sketch the graph, trace all, trace basically, trace the graph and move the point left or right and you will get the minima point on that graph also. I'll show you here. You can enter the equation. What is that equation? By the way, it is negative, sorry, the original function is 200 over r. So I'll write 200 by x plus 2 pi r squared. So I'll write 2 pi x squared. So this is the graph. Okay. Now on this graph, zoom out. And yes, you can find a point where we are getting what? Minima. Yes, here. This is the point. What is that point? 2.5154. That's the value of radius, right? And minimum surface area is going to be 119.26 something. By the way, for this question, they are not asking for the minimum surface area, but if they ask for minimum surface area also, this is the value. So using the graphical approach also, we are getting the same result. Okay, so simply draw the graph, trace the graph and look for the local minima. Next one. So that was by the graphical approach as well as second derivative test. Now let's discuss the same question with the help of second derivative test. How to find it? It's very simple and easy. All you have to do is first take your function. What is that? In this case, it was surface area. So A is your function. You already converted it in terms of one variable. That was 200 over r plus 2 pi r squared. Now find the derivative, which we already calculated. We got negative 200 over r squared plus 4 pi r. Now for the second derivative test, as you can see the name is there, we have to find the double derivatives. So what is the double derivative? Differentiate the function one more time. Okay, so I'm writing directly, I will get 400 upon r cubed plus 4 pi. Now all you have to do is find those critical numbers using above that. Okay, and in this case, what was the critical number? R is equal to 2.51 something. So now put this in that double derivative. See, if the double derivative at that critical number, okay, critical number, what is that? In this case, r is equal to 2.515 something. If the double derivative comes out as positive or negative, or there are three possibilities, 0. Okay. So if it is positive, then that point is the point of local minima. If the double derivative comes out as negative, then that critical number is the point of local maxima. And if the double derivative becomes 0, then this double derivative test fails. And we can go for either higher order derivative tests or back to the first derivative test. Okay, so let's check what we are getting over here. So in this question, when I substitute r as that value 2.51 something back to my double derivative function, you see, okay, so what I'm getting, obviously when I substitute that value over here, r as 2.515, the answer will be a positive quantity. Obviously there is no negative sign, right? 400 upon 2.5 something whole cube is positive, plus 4 pi is also positive, positive plus positive, positive. So basically positive is the answer. So double derivative positive, what is that? That means we are getting a point of local minima at radius is equal to 2.51 something. So in this way you can use the double derivative test also. The thing is, in the first derivative test, we are looking for sign of derivative thing, this. In the second derivative test, we are using the sign of double derivative simply, without drawing this graph table sign, right? This is second method. And third is the graphical approach also. We have already seen. You can trace the graph, find the maxima minima if calculator is allowed directly. So in this way, I explained all the methods. I hope you got all these. And if you still have any doubt, please feel free to ask me. Okay. So I'll see you all in the next session with our next topic. Thank you for watching this. Keep watching, keep learning.